Okay, so thank you very much. So to switch colours of hydrogen, we will now talk about the High Stories project, which is considering green hydrogen and how this might grow within the European Union to offer another commodity that could flow across the borders. And it's been great fun for me for the High Stories project. We are looking at how we can apply geological expertise that we learned with CO2 storage to hydrogen storage in the subsurface. And for me, it's been great to compare how these two things contrast and to see what we want from a CO2 storage site and what we want from a hydrogen storage site. And I've enjoyed the challenge and the expertise. So CO2 GeoNet was invited to undertake this assessment because we don't really have a European geological survey that has all of the data and all of the knowledge. But instead, the knowledge is distributed across Europe, and CO2 GeoNet draws this together to bring you the expertise to look at how we can consider storage of hydrogen. So there's lots in common. We're looking for good reservoirs, we're looking for a good seal, but there's differences in the depths that we're interested in. With hydrogen, we want it back. With CO2, we really don't. So we see that there are some competition areas and some areas where the two things are very complementary. So I'm going to tell you a little bit about the database that we have prepared in High Stories. So it's running from 2021 to 2023. We are collecting the data at the moment. We have it almost complete, and the database is being built and compiled and prepared, and we hope that this will be released very soon to show you the latest developments. So the aim of the database is to highlight regions and sites that might be suitable for development into geological storage sites for hydrogen. So it's been a significant effort from the High Stories project, and it's produced a comprehensive database with a broad coverage of almost the whole of Europe. So it advances the level of knowledge beyond CO2 stop and ESTMAP by making available the latest relevant geological data. You've seen a couple of presentations today that have talked about national initiatives that have brought lots of new data to the fore, lots of new data into the public domain, and in High Stories we have taken advantage of that to draw it together into one unified database. We also included hydrogen-specific criteria supporting assessment of the geochemical and the microbiological impacts that are specific to geological storage of hydrogen. So this improved database will enable more accurate assessments of the potential future for green hydrogen. And if you look on the bottom left, if you have worked in CO2 stop, you'll be very familiar with the relational database. So this is how we accommodate the different levels of data availability and the different levels of data confidentiality. So we start out with kind of a regional formation. So we know that there is a sandstone body here in this large basin that looks promising. We then narrow that down to potential storage units where we have a bit more data and where we can say, yes, we are confident that in this area there will be something. And finally, we break it down into traps. So we might have a specific closure in a saline aquifer, or perhaps a depleted or depleting hydrocarbon field that we can use. So this is how we try to accommodate the heterogeneity of data. And I have to say, it really does still show that we need to work together to try to make this data available. Something that High Stories has used is we've only used publicly available data. So the database will be able to be released, I hope, without too much trouble into the public domain towards the end of the project. So we built on the work of ESTMAP, which looked at energy storage in the European subsurface, and ESTMAP built on CO2 stop, which looked at CO2 storage in the subsurface. So ESTMAP considered other commodities with energy storage, including CCS and hydrogen, and CO2 stop focused very much on CO2 storage. So you can see, I hope, the colours are better on that screen than on this one. So you can see the countries in green that have been covered by High Stories. So the colours in green are covered by national experts in the country. In pink is where neighbouring countries have done an assessment. And I would like to say that Ukraine should also be green on this map, because we have very recently brought into the High Stories project a Ukrainian expert to help us assess an even greater amount of storage. So it's also worth noting, very importantly before I go on, that we've identified storage where the publicly available data tells us that it is present. So a lack of saying we've identified capacity does not mean that there isn't capacity. It just means we don't have the data yet to tell you that we can store CO2 there. And of course, for completeness, we have included some of the work on salt deposits, which was done in a previous project. So we haven't updated that because our challenge was to look at storage in porous media, but we want to include as complete database as possible at the end of the project. So what's in this database? So we have obviously some kind of name to identify each closure, some basic geological data. Those of you who did CO2 stop and SMAP, this will all look very familiar. And this is one of the joys of working in the subsurface. You realize that a lot of the questions we ask are the same. So for the high stories database, I want it to be useful after the high stories project for more things. So a lot of these sites could potentially be filtered for depth so that you could then consider CO2 storage, or you can consider natural gas storage. So I think the database will be useful after we've drawn all of the high stories conclusions. I think it will be useful to future research in Europe. So we have the basic geological data, some more reservoir data where it's available, pressure, temperature, net to gross, environmental deposition, mineralogy, if geological models and seismic data are available. And then this was the very high story specific aspect, was to look at geochemistry. So are there iron or sulfates or sulfides present that might react with the hydrogen? What about the presence of CO2 or other fluids which are going to react with the hydrogen? So with CO2 storage, obviously, we are disposing of that, it's gone, it's a long term away, but with hydrogen, we want it back. And so we're thinking very carefully about what quality of hydrogen will we get back out of the geological storage site. Of course, common to all fluid storage, we have to think about the leakage risks. Have we got a good cap rock? Are there any geological faults that might provide potential leakage pathways? How deep is this buried? And then we look at operational, so owner, production years, the wells and the vintage of these wells. As we heard earlier, if you're looking at old wells, you'd have to understand that they are well completed and they were abandoned in line with current procedures to be sure that those are going to seal, otherwise you'll have to go back and complete them again. So this was our data availability to identify potential storage sites. A very common theme you will see, so we have less data for the aquifers. But I think something that I'm going to steal for aquifers today, because coming from the UK, we're very fond of aquifer storage, is that the aquifers are available when you want them. But sometimes with reuse of oil and gas infrastructure, you might be a bit uncertain on the deadline. So I'm going to just throw that in there as one of my positives for aquifer storage. But here you can see the data availability. So we have good public domain data availability in a lot of cases, and we were able to find a lot of potential storage traps. So in total, we have 359 regional geological formations that look promising. Within that, there are 557 storage units where we have identified areas that are very promising, and 917 traps. And that's without us adding in the Ukraine data, which that work is still ongoing at the moment. So this is very good news, very positive for us, and the report and the geographic information system are coming very, very soon, especially looking at Arno, he's making sure that I try to keep to time when we're trying to collect all of these data. And I'm now going to hand over to Yann to tell you the next part of the story.
The second speaker is Yann de Gallo. He is a reservoir engineering working on CCS since 2000. He is now in Geostock and participates in numerous European projects, and is currently involved in hydrogen storage capacity estimate and modeling within the Asteris project.
Okay, thank you. So I'm going to show what I did with all these numbers, and that was collected by a lot of you. I crunched numbers, but I was looking at porous media to store with cap rocks, of course. And from the basing, I was only looking at the traps, because as Ceri said, we want to reproduce the hydrogen. The model is very similar to natural gas system. You inject and you reproduce what you inject, or most of it. So looking at this sparse data, we need to figure out how much hydrogen we can store in different countries in Europe. I will have to mention again that the data is not, it's scarce in some other countries. There are, at the minimum, a few required data, basic informations, thickness, porosity, depth, and anything else that could be provided in database, and sometime there is nothing. For example, for permeability in some countries, it's some fields or some aquifers, because lack of investigation in the past. So I needed to do some approximation, and get some idea of the uncertainties associated with these parameters. So with the minimum data set, out of the, I have more traps than Ceri because some of the underground gas storage are not in the database, so I did them. So all in all, I could compute about 790 capacities in different countries. But to compute the capacity, we need to have some approximation on the geometry of the traps. Could be a cube, it could be anything basically. So I assume that they were ellipsoids, so it's a simplification, of course. And we'll see how bad is this approximation. Then we can populate it with porosity and porosity distribution, I would say, net to gross, and this kind of information to compute the porous volume. Well, of course, this is mimicking the reality. And when you consider different storage or porous media that are available, you have, of course, underground gas storage are currently operating that could be readily converted to hydrogen storage, given the economics of it. Then you have the depleted oil and gas fields that are abundant in some countries, but not in all over Europe. Then you have the saline aquifers, potentially large, usually not very commercial, and poorly investigated, I would say. These different type of porous media have different issues in terms of hydrogen, be the reactivity, be the well materials, cement, and so on. So we try to classify based on the RSMS classification from SPE or the tiers from Strategy CCUS, how the different storage would fit in this classification, considering that underground gas storage could be almost a capacity, and the depleted hydrocarbon field could be a contingent capacity, and aquifers, well, takes much more work to qualify them. Then we need to compute the capacity, how much hydrogen can we store in there. Nobody has anything to besides running a site model. So I use the analogy with CO2 storage, where you have the capacity estimated based on the efficiency factor. You know the porous volume based on your geometry, where you have the geometric volume and the porosity. And then you need to estimate the, the efficiency factor. It will be different for the different porous media, whether you are in you have an hydrocarbon, you can assume that what you produce could be re-injected in terms of volume. For saline aquifers, of course, the properties are very different between CO2 and hydrogen, so you need to correct for the viscosity, for the density difference between the two different fluids. And for underground gas storage, you can consider that since they are operational, their storage capacity is their current gas storage capacity. Based on that, I compare this approach on published cases. Unfortunately, there are not that many of them for aquifers. So the first one is, and you see the distribution of the different parameters. In red is the volume in million standard cubic meters. In blue, it's the equivalent in terms of energy. And the black is the efficiency factor. And you see we have distributions of these parameters because of the uncertainties associated with the estimation of them. So we could get different values, mean, max, and the average, and compare that with published data from this aquifer. The computation are about right. So we are pretty happy with that. At least on that first case, we were quite close. Similarly, for a second aquifer, it's also in Poland, and this time it was published in terms of volumetrics, and we were very close to the average value of this published data that were computed based on reserve simulations. So when I compare that, we see that the approximation, despite the crude geometry, is fairly okay in terms of at this stage for this estimate. And then we could replicate this work for the 700 and so storage, and you have different type of storage here. The little black dots correspond to the gas storage. The size of the bubble correspond to the size of the storage in terms of energy. The big orange are the depleted gas field. The brown is the depleted oil field, and the blue are the aquifers, or deep saline formations. And there are the unknown or incomplete in some countries, which are the pink one. And over there, of course, the North Sea is a potentially very large storage area, but it would not be suitable for all the countries, unless you have a hydrogen backbone all over Europe, similar problem to CO2 storage, or to transport it. And you see that for the different type of porous media, the coverage is very different. For example, Spain has a lot of traps identified in terms of deep saline formation, similarly for Poland, and nothing in France. For the gas storage, for the depleted gas field, we have a lot in around the North Sea, in northern Germany, and nothing in Italy, for example. This was, but there are some production currently because of the lack of data, of publicly available data. When you sum everything, and that's at, in the bottom corner there, you see that we have very large capacity in the gas storage, in the gas field, much more than in the underground gas storage. But that supposes that they're all available and there's no competition with other activities and so on. So it's only capacity based. And this saline aquifer, the deep saline formation, it's very small. Of course, there is very little investigation of saline aquifer so far. So that doesn't mean, like Ceri was saying, that there is no capacity. That's currently there is no available data on that. So to stress again, our main conclusion so far is that, well, we find that there are gaps in the database, gaps due to publicly available data that are lacking in some countries. There is even for underground gas storage, there are some very different level of information. Sometimes, for example, for France, you don't get the storage capacity of one particular site. You get something that is merged together. So there's, all in all, there is quite a significant capacity. Well, the problem is when would that be available? It depends on the market. When would there be hydrogen production at that scale? What are the requirements for storage in the different countries? Because of security, strategy of the different countries. And well, if you need to develop, besides underground gas storage, it takes, the development time is quite significant, as we have seen this morning for CO2 storage. So with that, I would like to acknowledge the partners and the funding agency of the EU. And I didn't forget CO2 GeoNet parties that did contribute significantly to this work.